Thanks for coming, everybody. It's a great pleasure this morning for me to be able to introduce Tor Sverre Lande. Just call him Bosson, though, because that's what all his friends call him. He's from the Department of Informatics at the University of Oslo in Norway. Last time Bosson was visiting me, I think, was about 20 years ago when he had a great, huge land whale of an RV parked in front of my house with his 3 little boys and his nice wife, and we had a good time together. And we got to know each other working in Carver Mead's lab at Caltech back in the 80s, and see him on and off over the years. But this is some really cool stuff he's gotten into in recent years using analog VLSI to do some radio and radar work. Bosson, take it away.
Thank you, Nick. It's really a pleasure being here at Google. I'm not sure I fit in here, a little bit hardware-oriented things that I'm working with. So, but still, I hope you can appreciate it. I hope it's something that you haven't heard before, which it is all about impulse-based systems. Impulse, like we have in our nervous system, like small pulses in time, and that's it's all a little bit back to the future, because that's how it used to be in the old days. So for a start, I'd like to show you this little device here. You can see it's up here in front, which I'm really proud about. It's a impulse-based radar. There's a couple of different versions here. I have one that sort of peel off here, and this is a little newer version of it. Basically, it's all contained in one single chip there. In order to, because it's so easy to talk about these things, but in order to make you believe that this is not just talk, it's a real thing, I want to take the chance of giving you a demo of this little piece of hardware. And I've sort of running this radar in the most simplest mode. And I've tuned it for just one sort of distance. There's actually a number of different shells that are sort of going inwards towards the radar. See, if I'm moving here, you can see it actually detects me. And there's like one shell. I've tuned it to just one shell. You can see it up here. It's shell number 61. There's like 64 different shells going outwards and inward. And to illustrate the sensitivity of this little device, the problem is that my body is here as well, though. But if I sort of put my hand on top here, you can see that at some point here, it's getting really, really sensitive. You can see my hand is almost not moving at all right? So it's actually, you can see my hand, all right? Now, this radar, it's electromagnetics. It's radio waves. It's just sending pulses. There's one antenna that is emitting a pulse, and another antenna that's actually receiving this reflected energy from my hand. And compared to like Sverre, my hand is not a big thing though, but still able to get hold of my hand here. See, it's almost difficult to keep it still when I hit the sort of the sensitive shell that I've tuned it to just now. Now, the interesting thing about these kind of devices is that since it's electromagnetics, it's actually able to look through as well. So if I move under the table here, it's able to see my hand straight through the table. Can you see that? So I'm sort of moving my hand under the table here now, and it's able to see my hand through the table. And that's a nice feature. That's something we can use. So that's to illustrate that we're actually working with electromagnetics. Now, electromagnetics, they are kind of fast, okay? They're kind of fast. They're running not at speed of light, but close, like 70% or something like that, depending on what kind of medium. But in air, it's close to the speed of light. And at speed of light, it's kind of fast. So it's demanding. I mean, we're in the millimeter range here. See, it's almost difficult to keep my hand still. And the light is actually circling Earth 7.5 times each second. So when you have to detect millimeter wave sensitivity in distance measurements, that's something that demands really, really fast computation and processing. And I think this is unique. It's something that you can't buy. I mean, most radios today, they have like in the meter range of resolution. And this one has in the millimeter range resolution. That's why I think this is a unique technology. It's still quite immature because you see it's noisy, this data though, and there's a number of things that could be, by simple signal processing and processing on this kind of data. But these two properties of this little radar, it's quite important because we can look through matter, and we can sense changes, movements, with high resolution. And the last thing, which I consider both of these things has been done sort of before, but in addition, we managed to do it on 1 little square millimeter of silicon, in using almost no power. So the power we're sort of emitting with this radar is very, very little. The pulses are like 0.8 volts, peak to peak. The secret is the way we do it. So how do we go about making these kind of devices? And what I hope to show to you today is that these kind of devices, it's something which is actually quite suitable for current technology. We are sort of exploring properties of current technology, which is very useful. By the way, you can these I have to thank this small little company, startup company, Novelde, which have sort of made these things available to me. Some of the ideas is sort of my own, but there's this spin-off company to try to make these devices, and those are the things I'm using here. So what I'd like to take you guys through today is to figure out how can we do things. Actually, it's more the way we think of, the way we design. It's a matter of exploring technology in a novel way, okay? And I'll try to convey how it's possible to make these kind of high-speed processing, because like this radar piece here is actually running at 70 gigahertz, and that's a little faster than your Pentium. But the technology is still not that advanced. It's 90 nanometer. I mean, Pentiums, I think, is running at 45 nanometers these days. So there are some ways we can explore silicon to do not only these kind of sensors, which I call short-range radar, but also to do short-range communication in a different way. I mean, yet another wireless. It's not quite the same as the standard one, but I'll try to explain how we can get this through. So what I'm touching into today is sort of the thoughts, the way to think about designing these kind of silicon systems, and not so much sort of promoting this kind of products there. Now, first, to start out from the beginning, I mean, sparks or spikes, it's very old. I mean, that's what we have in our body, as I told you. I mean, nervous system is like spiky, you know that? And the first radio by Marconi was also a spark-based system. So impulse-based, spike-based system is a quite normal thing. What we should remember is that a spike in time, a very narrow spike in time, has a wide frequency content. There you go. So we have a wide frequency spectrum when we have these short spikes here. While compared to the traditional radio, where you have a carrier wave, it's actually a very narrow band in the frequency. I guess most of you guys knows these kind of fundamentals, though, but it's good to have in mind when you start to understand these kind of systems. Now there are different pulses. We can just send a pulse. Not there, you know. We have some pulses to choose about. We can make just like a square wave kind of pulse, but they seem to have a lot of noise in the sidebands. These cosine, half monocycle of a cosine is also good, and these sync pulses are making sort of like a brick wall appearance in frequency, which would be very nice though, but they tend to be difficult to make, these kind of sync pulses. So what most people do in these kind of impulse-based systems is making what we call a Gaussian-shaped pulse. And the Gaussian-shaped pulse is of course a Gaussian-shaped distribution, like this one is a Gaussian. But then we're not only using this sort of this original Gaussian pulse, we do use derivatives of this Gaussian pulse. So you have 4 different derivatives showing up here, or 3 derivatives. I won't go into details here, but we can explore these properties of the pulse to make, by changing the width, we can narrow the pulse the wider in frequency, and we can also play with the order. I mean, which derivative of the pulse we're using. So if we use a high order derivative, we can sort of take away the low frequency content of the pulse. So we're able to, by playing with these 2 parameters, we can fit whatever bandwidth we want to transmit in. Okay, these are the fundamentals of Gaussian pulse shaping. And the reason I'm telling you about it is that this notion of ultra-wideband, which was approved by FCC, I think, 2002, sort of gave us an opportunity to explore these kind of devices, even without a license. And it's quite interesting that the 3.1 to 10.6 gigahertz unlicensed bandwidth is actually the largest bandwidth ever released. It gives up some potential of doing interesting things with impulse-based systems. Now, one of the sort of things to take care of or to think about is the low energy emission. It's only minus 41.3 dBm you're allowed to transmit within 1 megahertz bandwidth. But that's one of the reasons that these kind of radio are interesting. Now, from my perspective, I have more or different, I should say, ideas of why it's interesting, because it gives me a new challenge of making new and interesting circuits, I guess. There are a couple of other things that we should it's quite different from the mostly frequency domain processing we're doing in traditional radio. It's like time domain things. It's also interesting because there's no carrier. It's carrierless communication. I mean, carrier means that carrier is actually not doing anything but carrying the information. So a carrier is actually, it's not actually transmitting any information. It's the modulation of the carrier in traditional radio. So the energy I'm putting into generating a carrier in a traditional radio is actually a waste of energy. So taking that away, it's sort of fundamentally to get rid of a power consumer in my system. I can do other different things, which is not that intuitive to see. Like one of the problems with traditional radio is interference. I have it reduced, or usually like 16 or 8. You know, on Wi-Fi there's like 11 or 13 channels, depending on where you are. So it's a reduced number of channels. And after all, if you look at Wi-Fi, it's actually 3 or 4 channels, non-overlapping. So it's very few channels. So a number of channels is actually a problem. With these kind of time domain systems, I can make 1,000 channels. And it takes a little time to show you why, but there's no free lunch after all. So if I make a large number of channels, I have to, but my penalty is the bandwidth. But that's on each channel. It's also interesting. There might be some indications that the penetration of these kind of radio arrays, impulse-based, are a little better. But one of the most important things is the improved sensitivity we're able to achieve. I mean, the radar I showed you here just a while ago, I mean, the amount of energy reflected from my hand when I'm holding it in front of the radar is very, very, very little. Now, how can I recover that? Basically, if you look at it on an oscilloscope, you don't see it. And if you just look at it without processing it, it's noise. And we have measured this radar here. It's actually able to recover energy or signals 1/10 of the noise floor, meaning very, very faint, small signals. There's no magic to this. The only thing we're doing, we're actually integrating. We are sending not only one pulse, but we are sending millions of pulses, right? So if you keep doing that for a while, you are able to sort of reduce your white noise by integration. So there's no magic to it. The important thing from this example is that we have solved, or our implementation enable us to make these kind of long integration, which used to be a problem with standard like analog integrators because they are lossy. But I'll explain that. It takes some. Nyquist tells you that twice you have 7.5 gigahertz bandwidth in my band, and I have to sample at least twice the bandwidth, 15 gigahertz. That's my sampling rate. For all practical purposes, I have to go up. So you can easily see that this is a demanding task to make these kind of circuits. So from my perspective, we need a new design approach, and that's what I'm trying to come up with here. I want to tell you about a new way of thinking, or it's not a new way, but it's a different way, I guess. That's what I think. We have to. Dick mentioned Carver Mead. He told me listen to technology, and I think that's a good advice. So what do we get out of silicon? What are we good at with silicon today? Now, what's really good is there are two things happening. We are getting down. We're getting down in power, and we're getting up in speed. Okay. So down in power means also lower supply voltage. You know, these chips, these processors today, they're running at like 1 volt. And that imposes a problem if you want to do like traditional signal processing, analog signal processing, because these low power supplies is actually limiting the quality of the signal that I can receive, all right? So if I try to do more other things than 0 and 1, which is the digital way of looking at the world, if I try to do like an analog measurement of some kind externally from a embedded silicon system, then I really need, it's really hard to do a good solution. So we should reduce on the demands on the value. But what we have wasteful of speed. We really have high-speed electronics. So if you look at this a little more systematic, we have like a digital, digital and analog. Like I guess I should use this pointer here so everybody can see it. So we have this analog approach and we have this digital. And in a pure digital domain, we have discrete values and we have sort of discrete time and we have binary values. Now in the analog domain, we have a continuous time and we have an analog or continuous value. But there are something in between. Of course, we have these sample data techniques, which I know that switch capacitors. But the one we're going to explore today is this, sometimes called neuromorphic coding. And I'll use another word for it today, continuous time binary value. So basically, we'll take away the clock, forget the clock. So let's go continuous in time, no clock. And let's stay digital in value. And that's what I say when I talk about listen to technology, what's best for my technology. So I think that's the optimal approach for scaling your system with technology. Explore continuous time and work with binary values. Just to show you an impulse transmitter, impulse radio transmitter. I think this is the only transistors I'm going to show you. But it's important for me not to show you the actual solution, but I want to show you something quite important with these kind of impulse systems, like the transmitter I have on this little radar. It's actually just 2 transistors and a delay. Again, I should use this pointer here, I guess. So it's just a delay here and 2 transistors. That's all there is. And you can imagine that these kind of very few transistors, usually we use millions of transistors, but making it that simple enables us to make very power efficient transmitters. And that's quite different from what we're used to in other wireless narrowband radio, because in your mobile phone, the time you can talk, it's much less than the time you can listen. All right? So you have a standby time, which is much longer. And that sort of reflects the fact that in most systems, most of the energy is burned in the transmitter, and little energy is burned in the receiver. In these kind of impulse radio systems, that sort of is reversed. And this is actually measured pulses. You can see it's like 0.8 volt peak to peak that measured. It's a first derivative of a Gaussian. Okay? And you can also see how it works. First, I just pull up, and then I pull down after a short period, which is given by this tau. Okay, I still need to keep using it then. And the nice thing is it scales to higher technology sort of nodes. So we can sort of adapt to high technology very easily with these kind of circuits. But that's all there is. I can scale it to higher derivatives as well. But that's basically what's all there is to do with this transceiver. It's so easy. Now, if you want to transmit some information, like in a wireless communication system, we're usually talking about we're transmitting symbols. And these symbols are coded as a pseudo-noise sequence. We want to try to make it, sort of spread it out in time in order to make a wide bandwidth. So we can't just send one pulse and say that's 1 bit. We have to send a number of pulses, which is named PN or pseudo-noise, in order to code like a symbol. Of course, my symbol could be 1, or it could be 0, or it could be A, it could be B, whatever your symbol you care to code your symbol. But usually you need at least 2 symbols. That's sort of but that could be sort of traded in as a number of channels. So this is how we make our channels. Either we can sort of fill this sequence of, so where there's a 1 in this sequence, so where I have a 1, so so all the 1s here reflect that I'm transmitting a pulse. Where there's 0, I'm not transmitting anything. And then I can sort of play with this sequence of pulses here. I can make them longer. If I make them longer, I can make them more sparsely, less filling. And if I have less filling, I can trade that in for more channels. That's how I make my channels. And I have to select codes, however, that are usually called orthogonal codes, so they don't interfere. And that means that one of the important issues of impulse radio is that we don't have fading or interference, or very little interference. And even we can use it constructively, what is called sort of multipath or reflected energy. So yeah, let's be a little faster. One of the issues we have to live with is the sort of difficult environment that we are living in. There are all sorts of sources for reflected energy around here. So like here, if I have a transmitter here, there's one path, the green one here, goes directly to there's something in between here, so that may be shaded from the actual receiver. There may be some walls or some whatever bits and pieces around here that actually reflects my energy. So what I see direct path, and I see direct reflected energy coming from the environment around me, especially indoor. Is that very problem that is known to affect us, and that if we work on that, it looks quite ugly. It's called a delay spread, what you see down here, And it's sort of reflect the amount of sort of energy coming from all around in the environment here. So my pulse is not only one single pulse, it's a lot of pulses that sort of reflects out in time. Now, if I have these reflected pulses out in time, they will look like this is my pulse, but what I see when I receive them, they will sort of appear several copies of them. Usually this is not quite right. They go down in energy, so they're getting smaller with time though. And if so this will be one single pulse, and we usually call this a chip. And if we combine it to a symbol, we see these sort of patterns repeated. They tend to be these patterns, repeated patterns, within one symbol, they tend to be the same, all right? Now, and we can explore that these symbols, the pattern, the PN pattern, appearing in time is actually repeated due to reflected energy. And we can try to explore that in order to recover our transmitted symbol. Those kind of receivers is actually called Rake receivers. I think it was published in 58 or something, 1958, that kind of architecture. So it's good old stuff. Now, the implementation of Rake receivers is known to be very power demanding. But you can imagine why. Because if I've sort of taken these pulses and I've sort of sorted them in time. So we have all these pulses here appearing with reflected energy in time, and they're sort of spread out in a random pattern. Now I have to look here. These boxes here represent different templates. There's 4 templates here, though I can get along with only 2, whatever I care. And then I have to look for these patterns in time. And that it's actually what is called a cross-correlation. Cross-correlation is sort of a demanding, it's a demanding computation. And it's not used too much, tend to go to frequency, just because it's so demanding. Because I have to multiply, at each point in time here, I have to multiply my template with my signal. I have to accumulate results over here to detect the probability of my signal my symbol appearing, and that has to be in a running fashion. So it's a sort of a running cross correlation that goes on. So I'm looking for that pattern all the time. I have to do it all the time. So I can't sort of sit still and just look for it when I care. I have to do it all the time. That's why it's known to be a difficult and hard task to do. There are some approximations to that. But we have to realize that this is actually a statistical operation. We have to think about the probability, because we can't count on that all these pulses will appear, because they're so small and so low intensity that they'll disappear into sort of in noise. So we have to look at these patterns, and we have to compute probabilities that they are actually appearing. It's known, as I said, to be very power hungry, but I'll try to show that this continuous time binary value approach is actually giving us a very power efficient way of implementing these boxes. The traditional way is actually you take a template. I'll try to explore, or I have to explain some of the problems here. Now, the traditional way is this is my receiver, and I multiply, if you like, with my template here. And then I have to, as my signals come in here, I have to sort of take one bit at a time, and I have to sort of sift through my template here in the correct, at correct time, all right? Now that's a sort of messy thing, because then I need to synchronize very accurately with my sender, and synchronizing. I mean, remember I said that we're sort of shaping our symbols as pseudo-noise, as appearing as noise. Now, how do you synchronize when on noise? That's fundamentally very difficult. So in one hand, we want to synchronize. On the other hand, we don't want to transmit frequency components, and that sort of kills us. It makes it really difficult to synchronize. So I'll propose a solution to that. So that's one synchronization problem. The other one is the sampling problem. I mean, if I really want to read the analog value of this signal here, I have to sample with a really high rate. So our solution, the solution of using a binary value, just a very coarse binary sampler, just put a threshold and check if my signal is below or above that threshold. That's sort of a very coarse quantizer. And that's something which is feasible. If you want to do more bits, it's really hard. So I'll try to present you a continuous time binary value solution. This figure has both the radar and the radio, though. So let's, if you look at the radio down here, the first thing we do, as I say, we have a very coarse quantizer. I call it zoom thresholder. I won't go into detail on that, but it's a sort of programmable thresholding element. I can set a couple of parameters to sort of hit the right where you want to be, because if you just take, you have to find your signal. So that makes it a little more complicated than just put a threshold. You have to put your threshold in a wise way. And then we'll stick to a continuous time. We'll just, so after here, we have a binary value, meaning zeros and ones. And zeros and ones we're really good at, because that's digital. And in continuous time, we'll binary value, we'll try to do some of the important processing. And then we'll end up with a low frequency standard sort of digital value. But we are getting rid of all the high frequency demands, like the high frequency sampling, and also the very precise synchronization, which is required in traditional approach using a DSP kind of solution. Now the SEM plates, I want you to just to think of it as an analog to binary converter. We can set a threshold here. Oh, sorry. It's slipping down here. You can set the threshold here, and then what's coming out in the other end here, it's just a high voltage or a low voltage, which represents zeros and ones in a normal way. If we want to make a Rake receiver, that means we get a stream of zeros and ones that we have to sift through or correlate with my templates. And in order to avoid the synchronization required in these systems, we make what we call a full rake. So we make a full Rake receiver, meaning that we are looking at all sort of possible occurrences of a pulse and try to cover all possible occurrences, meaning that we're not affected by the synchronization. I mean, we accept that it can appear anytime in time. I don't have to know when. And the trick is to use this structure that you see here, which is a very simple, very well-known structure. It's called a delay line. So my taus here are basically the fundamental, simplest thing that you can make is an inverter. And if I spread that out in time, I remember, I have the history of what happened. And that history could suitably be one of these chips. So all the span of how long I'm expected my pulse to live within. So we know there are some reflections, and we know the pulse is coming, and if the chip, we have a chip rate at which the pulses may occur. So if I make this delay line at least one chip rate, I'm sort of okay. I'm covering where I'm expecting my pulse to appear, and that chip rate we're talking about, it's the order of megahertz. It's not in gigahertz. It's like 20 to 40, 20 to 50 megahertz, which is a reasonable clock. It's a low clock. So if we now we can look at the history here by looking at these taps here of the delay line. So by reading out these taps here, we know the history of my signal. And if we sample those signals, those are zeros and ones. Now we are in the low frequency clock domain, meaning 20 to 50 megahertz or 40 megahertz. We are able to make a sequence of ones and zeros, which is actually the one bit sequence we want to recover for our symbol. So if we organize now, I have my continuous time, my bit stream coming in here in continuous time. This is continuous time, all delay lines. Now, if I look at all these, you can see the taps here. If I look at these taps and I clock them, so basically what I do, I fill up my delay line and then I sample. Then I fill up my delay line and I sample. All right. If I keep going like that, you'll see that we're actually getting the symbols, the running stream of symbols here at a little later little point in time, or a little actually earlier in time. I'll get a sequence of zeros and ones here, and that goes on. So I'll remember all the patterns. Now I can do this because these electronics, they're only what we call D-latches. They are very cheap to make. And there's another thing which is quite surprising, is that now the demanding multiplication, when I go to binary value, it's very simple. It's just an AND gate. So it's a very simple operation. So it's very, it simplifies my correlation computation. So I can afford to do all these fingers. I can afford to do a full rake if I simplify my multiplication. And that's what we do. So just to finish up, I hope I'll try to convey you some of the principle of continuous time binary value Rake Receiver, where we actually we quantize the input. We use a sample delay line, which is a continuous time thing. We make a full spatial Rake Receiver, and we avoid the synchronization problem because I can that pattern I'm looking for, that pattern, my symbol, it can appear in any of these fingers, okay? And which one doesn't really matter as long. And also, I look at all the reflections because some of these fingers may have reflections and some may have what we call usually line of sight signal. And I can combine all of them and look for my pattern in all these fingers. So I do what's called constructive interference. I can use my interference constructively to recover my signal, my symbol, right? So that's a nice thing. I'll finish up this part on impulse radio by just summarizing. We have a very simple, very low power, ultra low power transmitter. And we have a full continuous time Rake receiver, which is also low power. And we have sort of multipass detection, and we avoid all the sync problems. So by this, at least I give the background for making a very power efficient, lean transceiver of impulse radio in standard technology. Is that okay? I'll leave the questions to the end, but I'll do some of the radar stuff as well. The thing you saw here, say the best part to the end. This is also old stuff. Hulsmeyer, there's a patent from 1904 I figured out, where they actually, as for radio, they started out with impulses. Then, in the 1920s, everything was frequency. But also the radar actually started out with impulses. And that's kind of interesting. It was sort of explored and developed to be for long-range applications during the World War II. There are some recent defense work on ground-penetrating radar as well. There are some interesting work by Tom McEwen from, he used, I think it was a Lawrence Livermore lab in the early 90s. And he proposed something called micropower impulse radar, which is some of the stuff that caught me on this. A guy called Staderini from Italy made build this radar based on some of these patterns with discrete components. And this figure is actually from his publication. It sort of shows you the fundamental principle of radar. You have a pulse generator. We have a transmitter that sort of radiates the pulse on the target, and the reflected energy is sort of received here on the receiver. And then, since we're all in the same box here, we can sort of wait for a suitable amount of time, which is called the ranging. So we can change the range. We're sort of sampling in, and then we put in the sampler here. And this one has to be very fast. Usually you see speed recovery diodes and things like that. And then we do an integration. And all this were done with discrete components and analog sort of solutions in these first radars. But still, it's a very neat piece of work. So if you have time to look at it, I think it's great. But yeah, let me skip that slide just to. It's possible to look into a body with these kind of things. Stadarini proposed the idea of medical radar, and it's not too much attenuation. Like minus 35 dB is something that we can live with, depending on what kind of layers you're going through. These kind of different layers that we have in our body, it's also interesting regarding penetration and nonlinear penetration. But that's a topic I won't be able to cover here today. But it is interesting. I'll just explain you the continuous time binary value impulse radar. It's very similar, but the idea of these analog radars we had before, they were not feasible to implement on a digital process. So by exploring a continuous time binary value domain, we're able to do so. So we have a pulse generator. We send out a pulse as we see. So we recognize sort of the general topology of a radar. And we have a delay element here where we can do the ranging. Now, we do a little better these kind of integrated radars, because when we receive the received signal here, we have this input stage, which is basically a thresholding element. And instead of having just sample, since we threshold and we're a binary value here, but still continuous time, there's no clock. So all this is binary value continuous time. We have zeros and ones here. And zeros and ones is something we're really good at treating at high speed. Again, technology. So we can sample it. We can have more than one radar. So actually, compared to the McEwen radar, oh, sorry, what happened here now? Compared to the McEwen radar, we have something like 64 separate radars here, actually all working at the same time. The second generation here, I have here in my hand, is actually a 256 radars. What's also nice is that integration of these bits, it's kind of easy to do, because integration of bits is actually just counting. I'm just counting number of ones. So that, if you go in the signal processing world and talk about that, you will have something called a lossless integrator. I can integrate for a long time. And still I'm integrating, which is undoable in an analog domain. So this continuous time binary value gives me that opportunity. I can integrate for a long time. And that's why I'm able to recover these very faint signals that you see in this radar. All right? We had another approach, which I think it's quite important. We call it swept threshold sampling. A little bit difficult. I mean, basically, if we only set these blue things, could be different threshold voltages. So if we have a high threshold, we'll get this sort of dashed red narrow pulse here. If I have a low threshold, I have got to get this white pulse here. So depending on what kind of threshold I'm selecting for my thresholder, I'll get these different results. So we figured out, why not sweep the threshold? Start from some low value and then sweep it upwards and keep going. And if we start working a little bit on the theory, you see we're actually doing a full ATD conversion. And of course, if you look in literature, you find it. It's called ditted 1-bit ADC converter. So, but we do it a little bit differently, though. But it's a good idea. You actually map out, I mean, the value to any resolution with these kind of approaches. The theory, it's too, I won't go through it today. a little more elaborate how we do these things. So we have a digital pulse generator, so that generates a pulse. So I don't know, it's a sort of noisy pulse. I send it out as a Gaussian here on the antenna. And again, you find the delay here, which I can tune with a range. And you see what we do here, we only delay the clock input. The sampling time is sort of by, again, our familiar delay line. But this is a very high-speed delay line running at that gives us actually a close to 70 gigahertz in the latest implementation sampling or depth sampling. So these are the different counters, different integrators. So it will it gives me the different shell. You remember the shells I talked about around this radar? So those are the different integrators. The counters are actually different shells that I have in my radar. Why keep it moving, this stupid screen? I'm sorry for that. So that's more elaborate. One of the most intriguing results is actually these results, because they were unexpected. If you actually work with these kind of systems here, we can compare it like the behavior of these kind of very simple quantization systems that we have here. If we on the x-axis here, I have noise. So I start out without noise. But in any real transmission, there's noise. There's a lot of noise, and of course, it's all proportional to the amount of energy you're allowed to transmit. If I can throw out a lot of energy, there's no problem with it. So we have like a signal here, but we keep the signal stable and we increase the noise. Now you see the green lines here. They actually show that for an analog, when I have an analog. This is done in MATLAB. So when I have an analog signal, I don't need to integrate at all at low noise values. Now, as I increase the noise of my signal over here, you can see that there are sort of 3 different solutions here depending on the quality. Now, if you have one really high quality, I have to early start an integration here, and I have to integrate. So these are the number of integration. It's an analog scale. So these are the number of integrations that I need in order to recover my signal with some quality, okay? And I have 3 different qualities here. Now, the red ones here, those are what we call swept threshold sampling, our threshold sweeping technique in our radar. And again, we have 3 different sort of quality levels, quality measures of number of signal to noise ratio, if you like that old-fashioned term. And you see, I can't, with this coarse quantizer, I need a number of integrations in order to recover my signal. You see, I have to start with close to 100 for at least whatever quality, even high quality signals, I need 100 sort of integrations in order to recover my signal. Now, as we increase noise here, and here's what's important, as we increase noise here now, we see that the ideal, the best case, the best you can do, high resolution A to D conversion in noise, it's rising steeper than our swept threshold sampling technique. So for high noise values, we're actually doing almost as good as the ideal case, meaning that we don't need too many more samples or integrations in order to recover a signal. And that's surprising. That really shows that this makes sense. Now, if you look at the good old literature, you find out that people have thought of these things before. So these blue lines actually shows something called stochastic resonance. It was some theory from the 80s, I think. In physics, guys figure out that if you have something repeated, or if you do integration, you are able to recover signals buried in noise. And as you see, for high noise values, we are actually doing stochastic resonance sampling. So it's quite remarkable that we're actually doing almost as well as the best case. So what are these? I mean, communication, wireless communication is something you convey some value. But this device here, what is it good for? Well, we have. I mean, the first thing was medical radar. I want to sense my heartbeat and my breathing and things like that. And that's what Stadarini did with his first radar. And we thought that was a good idea because you can make it as a detached device. It doesn't. Most of the heart beating measurements devices. They have to be attached to your body somehow, and you have these straps you wear if you have these jogging things, and it's not nice. I mean, people don't like that. So if I could put it on back on my mobile phone and put it here and read my heartbeat, that would be much nicer. If I can put it in the back seat of my car, I can use it to warn me when I fall asleep, things like that. So those are useful applications. I mean, I get when I talk about these things, I get a number of ideas from people that think it's nice. Like we want to track a radar or a probe, a pill in your body. We can do that in millimeter resolution. It's a very accurate ranging devices using electromagnetics, which is also we're orders 2 or 3 orders of magnitude better than state of the art in that respect. So we have even a company looking at stress detectors for pilots, well, it's up to you. There's a number of this is a very immature or premature, I should even say, device which has to be polished, and it's a new technology, and it's actually 1 square little millimeter of silicon. So I think there's a lot. There's actually potential. So remember, it's not only one radar. It's actually all these shells, 256 shells that we have in these radars, and I mean I can easily make 2,000 shells if I care. So my last slide. What did you learn today? I hope I really got you on something that you didn't heard before. We can make an impulse radar in nanoelectronics, off-the-shelf, cheap technology. And we can make very low-power transmitter and also low-power receivers using continuous time binary value. And as I demoed for you here, with these new techniques, we're also able to make this web threshold sampling, which can be used which I think is RF distance measurements, is one of the achievements of these kind of technology. And also these kind of sensing things I expect to be useful for these devices. All right, I think that's about it. Thank you. How are we doing time-wise?
We have time for questions. There's a microphone if someone has a question to ask.
All right. Could you use the mic?
I was wondering if you could say a few words about antenna design, kind of what sets the scale, what sets the shape, that sort of thing.
Well, in the end, it's a trade-off between the kind of band. I mean, this one you see here, the first one we made, was a little low in frequency, 2.5 gigahertz center frequency, fairly wide band. So actually, it's not within the sort of defined bandwidth by FCC as it is now. We have this one is better. Now the penalty of going up in frequency is you reduce your penetration. So, but the advantage of going up in frequency is you can make smaller antennas, all right? You can still make small antennas for lower frequency, but your sort of efficiency is degraded. Usually you try to make some gain in your antenna. And you can make them, and this one is sort of, it's a shell thing. If I make different shapes on antennas like a horn, I can sort of direct my energy. And parabolic shapes. We are working with since these transmitters are so easy to make, we are actually working with an electromagnetic beamformer that makes it possible to focus energy without using very focused antennas, because focused antennas tend to be large. But these bow ties antennas seem to be working fine. I've tried with smaller antennas; they're also okay. So, but still, I mean, for making a really small device, the antenna is some of the issues we have to solve. I'm afraid it wasn't a very clear answer about what is the minimum size here, though, but you get an idea of the problems. All right?
Have you considered using codes that give you multiple correlation values instead of the bi-level correlation values as a approach to helping synchronization.
Well, tell you one more. What kind of codes? Basically, the codes we're using are orthogonal codes.
These would be sort of like the pseudo-random codes, but instead of a bi-level correlation, they would give you multiple value correlations.
Well, yes, but that's sort of the trade-off, that you can do that, just having more symbols. And that would give you higher bandwidth, but less channels. So that's what you like to trade. So that's, in the end, it's a trade-off. If you want, I can make high bandwidth systems with this kind, exactly as you suggest, by using more symbols simply, and that's something you can do. But if you want to go for more channels, then you want, basically it's the length of the code and your population of the code, things like that, that in the end trades off well, I guess the important message here is to convey that these kind of radio, it's easy to play with these parameters. It's easy to make longer symbols. And it's easy to make higher speed if you need it, or more channels if you need it. And I think that's quite different, because in a traditional radio, you have to sort of assign your channels very accurately with your modulation of each of the channels. So these radios are much more dynamic, I should say. Is that okay?
Thank you.
You've described a novel technique for low-power, short-range radio transmission and radar. I'm curious to know if you have a sense as to applications. You know, if somebody turned this into a communications link, where might it fit in to other short-range communication things in terms of power or speed or so on? I'm familiar with Bluetooth, with RFID, with 802.11. Do you have a sense of where this might find?
Sure. I think the key is that reverse power budget of these kind of radios. It's really low power transmitter, and more power depending on how you solve your receiver, right? And that gives a symmetry which makes it interesting for like implants, body implants, where we have you don't want to change your battery too often, basically. But also, like, in my opinion, the current RFID technology is very immature. And I think this is a much better technology for tags like RFIDs, because there are two reasons. It's very low power. You can even do power harvesting, easy. Not easy, but you can do it. Secondly, I have a much larger number of channels. So that simplifies all my protocols. I can go do some TDMA or CDMA kind of things. That's what they're doing today. In order to, if I'm running my grocery store and I'm coming with my 100 items, I can't just roll through today. See? But that's fundamentally is basically the limited number of channels available. You have to sort of do one at a time because they interfere. So I think there's a number of applications where these kind of properties can be explored. And there's a third sort of fundamental issue or property of these kind of devices. That's the sensitivity, which I showed you with this radar. Because I'm able to recover very weak signal. Now, there's a lot of project research going on for home healthcare, or even in hospital healthcare, where you actually take away the wires. Because if you get wired up, you can't move around. And that's even not good for you. It's good for you to move around. So if you take away wire in a medical kind of environment, you better make sure that what's supposed to go on that wire, it's conveyed wirelessly, right? And that's something that sort of guarantee is not good enough with the current systems. I imagine that with this kind of integrating kind of hardware, I can increase my sensitivity to be much better than traditional narrowband radio, okay? And that, I think, is important. There's no free lunch, so if I do integration, I lose speed, I lose bandwidth, data bandwidth. But most of these medical applications, it's bits per minute or something like that. It's very slow, all right? Mm-hmm. So okay, so these are some of the ideas. I've got a number of other suggestions which are more specialized there.
Thank you.
Okay.
So a lot of the design in the receiver seemed to be designed to reject multipath reflections as noise and harmful. But I wonder if you considered, or maybe you're using the state of that Rake receiver as information, so that maybe sensing something about the multipath reflections is a useful signal, maybe in medical radar.
Yes, that's usually known as making a channel model, making a model of your transmission channel, and try to it is a good thing to do. So if you can sort of predict and correct your incoming signal, but the penalty is it's demanding processing-wise. So the question is, how can we? I mean, I'm very prudent with technology. My aim is really low power solutions. So what does it cost me in order to do this kind of channel models and compensate for them my incoming signal? And it's done today. I mean, like ADSL, this broadband modems, they do that. But it's not free regarding power. Okay? All right, thank you.